Hello YouTube, my name is Neil and we're studying for the MCATs today. We're in the Organic Chemistry Review, Chapter 10, Nitrogen and Phosphorus containing compounds. Organic chemistry is the study of carbon-containing molecules, but as you've seen, carbon is not the only element that plays a role in organic molecules. Many of the functional groups we've explored up until this point also include hydrogen and oxygen. Together, these three elements make up 93% of the composition of the human body by weight. But other atoms also contribute to biomolecules. Nitrogen comprises 3.2% of body weight and phosphorus 1.0%. In this chapter, we'll take a look at some biologically important molecules that contain nitrogen and phosphorus. In addition to the amides explored in the previous chapter, amino acids also contain nitrogen. These building blocks of proteins are discussed in depth in Chapter 1 of Biochemistry. In this chapter, we review their structure and focus on laboratory methods for synthesizing amino acids. Finally, we turn our attention to phosphorus-containing molecules, which often are used to transfer energy or store genetic information. Amino acids, peptides, and proteins. Amino acids are dipolar molecules that come together through a condensation reaction, forming peptides. Larger folded peptide chains are considered proteins. Description: amino acids contain an amino group and a carboxyl group attached to a single carbon atom, the alpha carbon. The other two substituents of the alpha carbon are a hydrogen atom and a side chain referred to as the R group. The structure is shown in figure 10.1. Let's draw an amino acid. The alpha carbon with its 4 different groups is a chiral or stereogenic center. Glycine, the simplest amino acid, is an exception to this rule because its R group is a hydrogen atom. All natural occurring amino acids in eukaryotes, except for glycine, are optically active, and all are L isomers. Therefore, by convention, the fissure of projection for an amino acid is drawn with the amino group on the left, as shown in figure 10.2. L amino acids have S configurations, except for cysteine, which is R because of the change in priority caused by the sulfur in its R group. And in figure 10.2, we have an L amino acid and a D amino acid, but all amino acids on Earth are L amino acids. At least in eukaryotes. So let's also draw this simple amino acid. I guess this is basically glycine. And I guess what we don't have on here is the H on the alpha carbon. Let's also label the alpha carbon. How about that? And let's draw its fissure projection, which will be a COOH on top. H on the right, NH2 on the left, and R down at the bottom. Let's label this L amino acid. Properties. Should we also write down that all have S configurations except for cysteine? So glycine is when the R group is a hydrogen atom. So let's draw glycine. And let's draw cysteine too for good measure. Do we know cysteine? We don't know cysteine. We'll leave cysteine for now. All the other amino acids except for cysteine has an S configuration. All right, on to properties. Amino acids with their acidic carboxyl group and basic amino group are amphoteric molecules. That is, they can act as both acids and bases. Amino groups can take on a positive charge by being protonated, and carboxyl groups can take on negative charges by being deprotonated. When an amino acid is put into solution, it will take on both of these charges, forming a dipolar ion or Zwitter ion, as shown in figure 10.3. How an amino acid acts depends on the pH of the environment. In basic solutions, the amino acid can become fully deprotonated. In acidic solutions, it can become fully protonated. So, should we draw the Zwitter ion too? Let's draw the Zwitter ion. We already drew the amino acids. We're just going to draw an extra hydrogen on the nitrogen. Would give it a, let's do this over again. An extra hydrogen on the nitrogen would give it a positive charge. And deprotonating the carboxylic acid would give, or the carboxyl group would give us a negative charge. And that's not to mention that the R group itself can have a charge as well. Zwitter ion. Aside from these Zwitter ionic properties common to every amino acid, each one has properties defined by its R group or side chain. The 20 eukaryotic proteogenic amino acids are grouped into 5 categories: nonpolar, non-aromatic, aromatic, polar, negatively charged or acidic, and positively charged or basic. Let's write those down. They can be nonpolar, non-aromatic, aromatic, polar negatively charged or acidic and positively charged or basic. Nonpolar aromatic amino acids tend to have side chains that are saturated hydrocarbons. Hydrocarbons are nonpolar. Like alanine, valine, leucine, and isoleucine. They also include glycine, proline, which is cyclic with a secondary amine, and methionine, which contains sulfur. Aromatic, so proline is cyclic, but it's not aromatic. What does proline look like? Right, so it's not aromatic, it's just a ring with no double bonds. It's a 5-carbon or a 4-carbon, a 5-member ring. And so, right. So aromatic amino acids include tryptophan, phenylalanine, and tyrosine. Nonpolar amino acids, both non-aromatic and aromatic, are also hydrophobic and tend to be sequestered in the interior of proteins. Polar amino acids tend to have terminal groups containing oxygen, nitrogen, or sulfur. These include serine, threonine, asparagine, glutamine, and cysteine. Negatively charged acidic amino acids include aspartic acid and glutamic acid. These amino acids have terminal carboxylate anions in their R groups. Finally, positively charged basic amino acids include arginine, lysine, and histidine, have a protonated amino group in their R groups. Polar, acidic, and basic amino acids are all hydrophilic and tend to form hydrogen bonds with water in aqueous solution. Amino acids undergo condensation reactions to form peptide bonds. The molecules these bonds form, called polypeptides, are the basic unit of proteins. The reverse reaction, hydrolysis of the peptide bond, is catalyzed by a strong acid or base. Both of these reactions are shown in figure 10.4. And we have 2 amino acids, and we have a peptide bond forming between the carboxyl carbon of 1 and the nitrogen, the amine of the other. Amino terminus, carboxy terminus. The reverse reaction of the peptide bond formation is hydrolysis. All right, like other carbonyl-containing functional groups, amides have 2 resonance structures, as shown in figure 10.5. The true structure of the amide bond is therefore a hybrid of these 2 structures, with partial bond character between the nitrogen atom and the carbonyl carbon. This double bond character limits rotation about the carbon-nitrogen bond, which adds to the rigidity and stability of the backbone of proteins. The single bond on either side of the peptide bond, on the other hand, permit free rotation. So peptide bonds have some resonance structure that gives it a partial double bond character. What makes glycine unique among amino acids? That it is not chiral, because around its carboxyl carbon, or carbonyl carbon rather. What's the difference between carbonyl and carboxyl again? What's carboxyl? The main difference between carbonyl and carboxyl is that carbonyl consists of a carbon atom double bonded to an oxygen atom, whereas carboxyl consists of a carbonyl and a hydroxyl group bonded to each other via the carbon. So ketones and aldehydes are carbonyls. Carboxyl acids are carboxyl. All right. They're saying it's carbonyl. It's also carboxyl. So what makes glycine unique is the carbonyl or carboxyl carbon being attached to two hydrogens, and so it's not chiral. 2. Amino acids are amphoteric. What does this mean? What functional groups give amino acids this character? Does amphoteric mean that it can both be acidic and basic, or positive and negative ions? They can act as both acids and bases. Zwitterion is that they can take on both positive and negative charges. Amphoteric is the acidity. What functional group gives amino acids this characteristic? I guess the amine can take on positive charges, or can take on protons, and the carboxylate can lose protons. Number 3, how are peptide bonds formed and cleaved? Peptide bonds are formed via a, I'm assuming addition reaction. Is it a substitution reaction? Because this oxygen does leave, presumably as water. Condensation reaction, rather. Condensation also involves the release of a small molecule, the loss of a small molecule like water. So yeah, oxygen via water. And how are they cleaved? By hydrolysis. 4. Why is the carbon-nitrogen bond of an amide planar? Because of the resonance with the carboxyl group gives it a partial double bond character which fixes it in place, prevents it from rotating like a free single bond. Synthesis of alpha amino acids. Before we go on, I wanted to put these into a better graph. They gave us so much information here. So let's do this over again. And we can go through some of these amino acids one more time. Non-polar, non-aromatic tend to have side chains that are hydrocarbons, like alanine, valine, leucine, isoleucine, glycine, proline, methionine, and that's it for nonpolar non-aromatic. Aromatic includes tryptophan, phenylalanine, and tyrosine. Nonpolar amino acids include nonpolar. Oh, that's not a classification, but nonpolar amino acids, both non-aromatic and aromatic, are also hydrophobic and tend to be sequestered in the interior of proteins. Polar amino acids tend to have terminal groups containing oxygen, nitrogen, and sulfur. These include serine, threonine. So after aromatics was negatively charged or acidic, but they're just going to polar because all the acidic and basic are polar. No, negatively and positively charged are not polar. Negatively positive charge and polar all are water soluble. But aromatics, both non-aromatics, nonpolar amino acids, both non-aromatic and aromatic. So both the aromatics and non-aromatics are nonpolar. Next classification is polar. So let's write down that these two are nonpolar. So the polar compounds, amino acids are serine, let's try that again, 3O asparagine, glutamine, and cysteine. Negatively charged, acidic. Amino acids include aspartic acid and glutamic acid. The acids have carboxylate anions in their R groups, makes sense. Positive or basic amino acids include arginine, lysine, and histidine. They have protonated amino groups in their R groups. Polar, acidic, and basic amino acids are all hydrophilic and tend to form hydrogen bonds with water. Let's write down that they're hydrophilic. All right. Synthesis of alpha amino acids. Synthesis of amino acids occurs by an astonishing variety of mechanisms in vivo. In the lab, several simple reaction mechanisms are exploited to make amino acids neatly and efficiently. Strecker synthesis. In the Strecker synthesis, one starts with an aldehyde, ammonium chloride, NH4Cl, and potassium cyanide, KCN, as shown in figure 10.6. The carbonyl oxygen is protonated, increasing the electrophility of the carbonyl carbon. Then, as seen in Chapter 6 of Organic Chemistry, ammonia can attack the carbonyl carbon, forming an imine. The imine carbon is also susceptible to nucleophilic addition reactions, thus the Cn- anion from KCN attacks, forming a nitrile group, a triple bond between carbon and nitrogen. The final molecule at the end of step 1 is an aminonitrile, a compound containing an amino group and nitrile group. This is how we make amino acids in the lab. Strecker synthesis. Let's look at the diagram and we'll actually draw it out. Oh wow, there's a couple steps. That's just step 1. Step 2. In step 2, the nitrile nitrogen is protonated, increasing the electrophilicity of the nitrile carbon. This is similar to protonating the oxygen of a carbonyl. A water molecule attacks, leading to the creation of a molecule with both imine and hydroxyl moieties on the same carbon. This imine is attacked by another equivalent of water. A carbonyl is formed, kicking off ammonia and creating the carboxylic acid functionality. This step, shown in figure 10.7, is performed in aqueous acid and can be accelerated by the use of heat. So we're going to draw both Strecker synthesis step 1 and 2. We'll draw some arrows in. We're going to draw some red arrows. So first we have, what did we start with? An aldehyde, ammonium chloride, and potassium cyanide. So, first step, the aldehyde, the carboxyl oxygen on the aldehyde attacks carbonyl oxygen on the aldehyde attacks one of the hydrogens on the ammonia. We get a positively charged carbonyl oxygen, and we have nitrogen, lone pair on the nitrogen attacking the carbonyl carbon. We have the carbonyl opening up, and then we have loss of hydrogen. So the OH, the hydroxyl, hydroxyl group, right? Yes, the OH, the hydroxyl group, grabs an extra hydrogen from the nitrogen, and then our carbonyl closes back up as water leaves, but this time it's not with oxygen, it's with nitrogen. And then we have let's see their explanation a little bit better. So first the carbonyl oxygen is protonated. Then ammonia attacks a carbonyl carbon, forming an imine. The imine is also susceptible to nucleophilic addition reactions. Thus, the cyanide anion attacks, forming a nitrile group. The final molecule at the end of step 1 is an aminonitrile, compound containing both NH2 and a nitrile bond, a triple bond with nitrogen. In step 2, the nitrile nitrogen is protonated, increasing the electrophilicity of the nitrile carbon, this carbon. This is similar to protonating the oxygen of a carbonyl. A water molecule attacks, leading to the creation of a molecule with both imine and hydroxyl moieties on the same carbon. This imine is attacked by another equivalent of water. A carbonyl is formed, kicking off ammonia and creating the carboxylic acid functionality. This step, shown in figure 2.10.7, is performed in aqueous acid and can be accelerated by the use of heat. So in the second step, the nitrile gets protonated. Water attacks the nitrile carbon, kicks off the ammonia. I guess after a second water molecule attacks. So one water molecule attacks, a second water molecule attacks, and then as a carbonyl or carboxyl double bond reforms, ammonia gets kicked out. So at the end of our first step, let's label this an ammonium nitrile. Aminonitrile, rather. Aminonitrile. And in step 2, we'll draw this out. We start with our aminonitrile, H2N bonded to a carbon and an R group, and that carbon is also bonded to another carbon that is triple bonded to a nitrogen. And that's our nitrile, our cyanide, our what do we call it? Yeah, our nitrile is this carbon and nitrogen, triple bonded to each other. The nitrile nitrogen gets protonated. Oops. Once it's protonated, it can get attacked by water. And then it gets protonated again. And then water attacks again. This time, our double bond. So in the first water attack from water, our nitrile, our triple bond, turns into a double bond. The second attack of water, our double bond turns into a single bond with nitrogen. And so I didn't realize how long this was. I should have made more room. That was good. Finally, our carbonyl reforms as ammonia gets kicked out. And then I suppose we could deprotonate our carbonyl. To get our carboxylic acid. All right, draw some arrows. And I did miss a step. The reshuffling of these hydrogens. I got the reshuffling of these hydrogens, but I forgot these. So let's move these around a little bit. So after the second attack of water, we got to lose or reshuffle our hydrogen a little bit. Or we have a hydrogen on the hydroxyl group or we have two hydrogens on the hydroxyl group. One of those is going to go over to the amide. R and H2. And arrows. Red arrows to show In the first step, the nitrile nitrogen getting protonated, water attacking the carbonyl carbon. No, not the carbonyl carbon, the nitrile carbon. And one of those triple bonds opening up. And then we have a second attack of water over here. And then that imine. So here, why don't we also label this an imine? Because the nitrile is the triple bond, the double bond is the imine. Or is that in the first step, the imine? What's an imine? So an imine is a carbon-nitrogen double bond. There's an imine up here as well as down here. Do you also label this an imine? All right, back into an imine. After the second attack of water, we have a carbonyl reforming. Right here. And our amine, our amino group, or our amine group, leaving. Right? Right. All right. It's a complicated little synthesis. All right. All right. The starting material for the Strecker synthesis is a planar carbonyl-containing compound. Therefore, the product of this pathway is a racemic mixture. The incoming nucleophiles are equally able to attack from either side of the carbonyl. Thus, both L and D amino acids can be generated through this process. Gabriel synthesis. Another way of synthesizing amino acids is the Gabriel or malonic ester synthesis, shown in 10.8. Gabriel. Synthesis. Strecker synthesis, Gabriel synthesis. Potassium Thalamide and diethyl bromomalonate. An amino acid is generated from thalamide and diethyl bromomalonate using two SN2 reactions, hydrolysis and decarboxylation. So we start out with SN2. And give it another SN2. And then hydrolysis, and decarboxylation. In this method, potassium thalamide is reacted with diethyl bromomalonate. Thalamide is acidic and exists in solution as a nucleophilic anion. Diethyl bromomalonate contains a secondary carbon bonded to bromine, a good leaving group. This setup should sound much like the SN2 reactions discussed in Chapter 4 of Organic Chemistry, with thalamide as the nucleophile, the secondary substrate carbon as the electrophile, and bromine as the leaving group. This reaction generates a thalamidomalonic ester. Thalamidomalonic. Consider the benefits of using such a large nucleophile. The bulkiness of this group creates steric hindrance, which prevents the substrate carbon from undergoing multiple substitutions. Instead, in the presence of base, this carbon, which is the alpha carbon between two carbonyls, can easily be deprotonated. The molecule as a whole can then act as a nucleophile, attacking the second carbon, or the substrate carbon of a bromoalkane. This is another example of an SN2 reaction. The nucleophile is the large deprotonated thalamidomalonic ester. The electrophile is the substrate carbon, and the leaving group is the bromide anion. And it's not over. Next, this molecule is hydrolyzed with strong base and heat, much like converting a cyclic anhydride into a dioic acid. The thalamide moiety is removed as phthalic acid with 2 carboxylic acids. The malonic ester is hydrolyzed to a dicarboxylic acid with an amine on the alpha carbon. Finally, this dicarboxylic acid, which is a 1,3-dicarbonyl, can be decarboxylated through the addition of acid and heat. The loss of a molecule of carbon dioxide results in the formation of the complete amino acid. Like the Strecker synthesis, the Gabriel synthesis starts with a planar molecule, thus the product is a racemic mixture of L and D amino acids. All right. I am going to try to draw this synthesis. Because there's so many steps, they don't draw the mechanisms for each step, which is nice. But we should be able to figure that out on our own. That'll be a good exercise. But we'll start with potassium thalamide, which has a benzene ring attached to a five-member amide. Thalamide. Let's look up thalamide. We learned that in one of the last couple chapters. Thalamide is this structure. I got a minus charge and a K plus charge plus Br attached to C, attached to H. The C's also got a CO2, C2H5 on the bottom, and a CO2, C2H2, or H5 rather, at the top. This undergoes an SN2 reaction. And where is the bromine? So the bromine's not here anymore. The bromine left as a leaving group. So this is our thalidomidmalonic ester. This is going to be our phthalimide attached to a carbon with a bunch of steric hindrance on it. So that's our thalidomidmalonic ester. Then we're going to add a base. To deprotonate our substrate carbon. Oh no, the bromoalkane is our substrate. So the R group that we're trying to attach to this carbon here. So basically we have a carbon attached to a bromine. I guess it's a bromomalonate. And we're going to lose everything except for the carbon. The carbon's all we really want. And the R group we add in the second reaction. Oh, we also want the nitrogen off of this in the end. This is a complicated synthesis. Okay. So after the base is added, presence of a base, the alpha carbon is deprotonated. And a bromoalkane, an alkane is added. So our next step is after the base. We have deprotonated our alpha carbon. And then the R group that we're trying to attach in an SN2 reaction. Another SN2 reaction to make our Did you give this a name? We'll see in a second when I turn the page. And then an AOH, an H2O. Then after water in the base, you get almost an amino acid. You get something with CO2s on them, 2 CO2s on them. We're going to, I guess, cleave one of them off and make it a carboxyl. And in the last step, we're adding acid in heat to get rid of one of those CO2s to end up with our amino acid. All right. Follow the description again. This is another example of SN2. So after the second addition, or the second SN2 with the R group, next the molecule is hydrolyzed with strong base in heat, much like converting a cyclic anhydride into a dioic acid. The thalamide moiety is removed as phthalic acid with 2 carboxylic acids. So this is phthalic acid. Let's write that down. The malonic ester is hydrolyzed to dicarboxylic acid with an amine on the alpha carbon. And our malonic ester the thalamide moiety is removed as phthalic acid. And I forgot the P in phthalic. P-H-T-H-A-L, So, P-H-T-H-A-L-I-C, phthalic acid. The malonic ester So this is a malonic ester. So the malonic ester is hydrolyzed to a dicarboxylic acid with an amine on the alpha carbon. Now, so this was a malonic ester. This is a dicarboxylic acid. This is also a dicarboxylic acid, except it's phthalic acid. This was our malonic acid. Our malonic ester, rather. So did I get the names of all these molecules pretty good? Thalamido malonic ester. I got that part. All right. Finally, this dicarboxylic acid can be decarboxylated with acid and heat. To make an amino acid, decarboxylation. Let's write down what the names of the reactions are as well. This is decarboxylation. This is hydrolysis. This is already labeled SN2. First one's also SN2. This is just being deprotonated. Simple enough. All right. What are the four reactants in the Strecker synthesis of an amino acid? Strecker synthesis takes an aldehyde, ammonia, a nitrile like potassium potassium cyanide has a nitrile. So potassium cyanide, and then water, I guess, is all you need after that. What are the reaction types used in the Strecker synthesis? The reactions are Well, water leaving, dehydration or condensation, specifically dehydration, as well as, so first, we have a nucleophilic or electrophilic. This is negatively charged, this is positively charged. Let's double check the first reaction of ammonia. This is nucleophilic addition. First step is nucleophilic addition. Then we have dehydration or condensation. And then another nucleophilic addition. In step 2, we have water attacking, so hydration. So I guess just hydration? We'll go with hydration. Number 3, what are the 4 main reactants in the Gabriel synthesis of an amino acid? The reactants in the Gabriel synthesis are thalamide, potassium thalamide in this case, a malonate, bromomalonate in this case, an alkane that we're trying to add as an R group, and that's all the reactants. We're still going to use NaOH, H2O, H3O in the next step. What are the reaction types used in the Gabriel synthesis? SN2, hydrolysis, and decarboxylation. Let's check those answers. (10.2) An aldehyde, ammonia chloride or ammonia, potassium cyanide for the cyanide are used to make the amino nitrile. Water is used to hydrolyze the amino nitrile to form the amino acid. Did we write down where the amino nitrile? Yeah, amino nitrile. Two, Strecker synthesis is a condensation reaction, formation of an imine from a carbonyl containing compound and ammonia with loss of water, followed by nucleophilic addition of the nitrile group, followed by hydrolysis. Three, Gabriel synthesis begins with potassium thalamide and diethyl bromomalonate, followed by an alkyl halide. Water is then used to hydrolyze the resulting compound to form the amino acid. While acids and bases are used at various times as catalysts, they are not main reactants. Number 4, Gabriel synthesis proceeds through two SN2 reactions, hydrolysis and decarboxylation. Great. 10.3, phosphorus containing compounds. All right. Phosphorus containing compounds. Phosphoric acid is an extremely important molecule biochemically. This molecule forms the high energy bonds that carry energy in adenosine triphosphate, ATP. Description. In a biochemical context, phosphoric acid is sometimes referred to as a phosphate group or inorganic phosphate, denoted Pi. At physiological pH, inorganic phosphate includes molecules of both hydrogen phosphate, HPO4, and dihydrogen phosphate, P2H2PO4. Biphosphate. They don't call it bisulfate like biphosphate like bisulfate. Call it dihydrogen phosphate. All right. I'm just going to write phosphate is denoted Pi. At physiological pH, inorganic phosphate includes molecules of both hydrogen phosphate and dihydrogen phosphate. So it's both HPO4 and H2PO4. The HPO4 has a -2 charge, while the H2PO4 has just a -1 charge. In addition to the energy-carrying nucleotide phosphates, phosphorus is also found in the backbone of DNA in phosphodiester bonds, linking the sugar moieties of the nucleotides, as shown in figure 10.9. So this isn't for amino acids, but this is for DNA. Phosphodiester bond. Let's draw a phosphodiester bond. A phosphodiester bond is between two sugars. We have a sugar connected to one oxygen on the phosphate, another oxygen on the phosphate is connected to the other sugar. And then attached to these sugars will be some kind of amino acid as well. Nitrogen, nitrogen, and H2. And we have a 3-end and a 5-end. In this diagram, 3-end on top, 5-end on bottom. Now, I guess 5-end on top, 3-end on bottom. It's just the 5-end is connected to our phosphate, or our phosphate in our phosphodiester bond is connected on top to the 3, on bottom to the 5. But for that sugar, the 3 is on bottom, the 5 is on top. This is like a 5 to 3. It looks like 5 at the top, 3 at the bottom. All right, phosphodiester bond. When a new nucleotide is joined to a growing strand of DNA by a DNA polymerase, it releases an ester dimer of phosphate referred to as pyrophosphate, P2O7, denoted PPI, and shown in figure 1010. The hydrolytic release of this molecule provides the energy for the transformation of the new phosphodiester bond. Pyrophosphate is unstable in aqueous solution and is hydrolyzed to form 2 molecules of inorganic phosphate, which can then be recycled to form high-energy bonds in ATP or for other purposes. So for good measure, let's also draw our PPI, our pyrophosphate. Which is also P2O7 with a -4 charge. Pyrophosphate is going to have 2 oxygen phosphorus double bonds on different phosphorus, and oxygen between the phosphorus, and additional oxygens on the phosphorus. So 1 double bond to an oxygen, 3 single bonds to other oxygens. 1, 2, 3, 4, 5, 6, 7 oxygens in total. 4 minus charge, -4 charge. There'll probably be a negative charge on this oxygen, this oxygen, this oxygen, and this oxygen. This oxygen has 2 bonds. These 2 have double bonds. It's these single bonds to oxygen that'll carry all the charge. And they're unstable, so they're going to break up into individual phosphates anyways. or individual, phosphates. Properties are nucleotides such as ATP, GTP, and those in DNA are referred to as organic phosphates due to the presence of the phosphate group bonded to a carbon-containing molecule. So while this is the inorganic phosphate separately, when it's in phosphodiester bond, it's organic phosphate. ATP, GTP, and DNA are referred to as organic phosphates. So PI, just the phosphate separately, is inorganic. In ATP, though, adenosine triphosphate, it is attached to adenosine, it's attached to a carbon-containing molecule. It's organic. Properties. Phosphoric acid is unique in that it has 3 acidic hydrogens, each with its own pKa. Phosphoric acid most properly refers to the form that predominates in strongly acidic conditions, H3PO4. In mildly acidic conditions, it loses a proton to become dihydrogen phosphate, H2PO4. It will readily lose a second proton to become hydrogen phosphate, HPO4, in weakly basic solutions. The form that exists in strongly basic solutions is phosphate PO4. The pKa for the loss of the first hydrogen is 2.15. For the second is 7.2. For the third is 12.3. At a physiological pH of 7.4, this means that dihydrogen phosphate and hydrogen phosphate predominate in nearly equal proportions. This variety of pKa values also makes phosphates good buffers because they can pick up or give off protons depending on the pH of the solution. Adjacent phosphate groups on a nucleotide triphosphate experience a large amount of repulsion because they are negatively charged. This, combined with the ability of phosphate to stabilize up to 3 negative charges by resonance, means that the energy released when a phosphate or pyrophosphate is cleaved is quite high. Great. What characteristics of inorganic phosphate make inorganic phosphate so useful for energy transfer biologically? I guess the repulsion between the negatively charged portions that are resonance stabilized. 2, what is an organic phosphate? Organic phosphate is when it's attached to DNA or just adenosine to make ATP. What characteristics of phosphoric acids make them good buffers? Its ability to pick up or lose multiple hydrogens. It can have 3 hydrogens, 2 hydrogens, 1 hydrogen, or no hydrogens. Let's check those answers. 10.3. Inorganic phosphate contains a very negative charge. When bonded to other phosphate groups in a nucleotide triphosphate, this creates repulsion with adjacent phosphate groups, increasing the energy of the bond. Further, inorganic phosphate can be resonance stabilized. Organic phosphates are carbon-containing molecules with phosphate groups. The most common examples are nucleotides, like those in DNA, ATP, or GTP. The 3 hydrogens in phosphoric acid have very different pKa values. This allows for phosphoric acid to pick up or give off protons in a wide pH range, making it a good buffer over most of the pH scale. Great. Practice questions. All right. Number 1. Which of the following amino acids does not have an L enantiomer? Well, and the options are cysteine, threonine, glutamic acid, and glycine. The answer's got to be glycine because it does not have a stereocenter, so it cannot have enantiomers. It is not chiral. 1D, glycine. 2. Which of the following would be formed if methyl bromide were reacted with phthalimide and followed by hydrolysis with an aqueous base? Well, if we tried to react the methyl bromide with the phthalimide before we do this, so if we react our methyl bromine with the phthalimide without this part, then it'll just attach to a different carbon. It'll attach to the carbonyl carbon. It'll want to attach to the carbonyl carbon. I think they even discussed that. Let's review what they said. The bulkiness of this group creates steric hindrance, which prevents the substrate carbon from undergoing multiple substitutions. So I don't think it's a multiple substitutions part. What would happen if we tried to do an SN2 reaction with this methyl before doing this? Instead of attaching to this carbon, it'll choose one of these carbons. So is that an option? So which of the following would be formed? It would be, I could tell you what it would look like. Let's draw it out, and then we'll figure out what the formula is for it. NO. We're going to attack this with an R. Br is a good leaving group. R is the electrophile, N is the nucleophile. Oh no, so I don't think you will get it attacking this. N will attack the R. Br will leave. So, in this case, our R is just a carbon. Just a CH, 3 in this case. Oh, and followed with hydrolysis and aqueous base. So the hydrolysis and aqueous base gets rid of our thalamic moiety. So we just have N attached to R without the C's. Whoops. There's probably some H's over here. That makes sense. Let's go NH2. NH2CH3, something simple like that. C2H5, where do they get the second carbon from? Because we're not even doing this step. So that's the wrong answer. C2's got to be the wrong answer. 4 methyls attaching. They did say that to prevent multiple substitutions, right? Undergoing multiple substitutions. I don't know why you have the BR though. I think both of the C2H5s are wrong answers. So it's between CH3NH2 or CH3 times 4N. You go with CH3NH2. Because I don't know the mechanism for more. I guess if you just deprotonated, you could get negative charge. Use it as a nucleophile to attack other, and it'll keep attacking. So is that in base, in aqueous base, followed by hydrolysis and aqueous base. So that would be the aqueous base part. Yeah, hydrolysis and aqueous base. But after hydrolysis, this is negatively charged. And it doesn't go anymore. No, yeah, that's in a different step. Adding the R is in a different step. So it's not going to happen multiple times. It's just going to happen once. It's just going to be B, is my guess. All right, 3. Which of the following amino acids contains sulfur? Cysteine, serine, methionine. I think just methionine, because that's the only one that they said. But that's not an option. So one of the other one has it too. Does serine also have it? Maybe they said serine does too. Serine, threonine, asparagine, glutamine, cysteine, which contains sulfur, methionine. Methionine, serine. Threonine and cysteine are both in polar amino acids, tend to have terminal groups containing oxygen, nitrogen, or sulfur. But they don't tell us which one. So what, are you supposed to look it up on your own? Let's look up serine. Doesn't look like it has sulfur in it. What's the other one we're looking for? Cysteine. Cysteine has sulfur in it. There you go. Oh, not cysteine. Cysteine, right. Cysteine and methionine. 1 and 3. B. Four, nylon, a polyamide, is produced from hexane diamine and a substance X. This substance X is most probably, polyamide is produced from hexane diamine. So there's your amine. And a substance X. The substance X is probably a carboxylic acid. Because we got the amine, we just need the acid. Not ketone or alcohol as much as acid, right? 4B. That's what we were using in these syntheses. 5. Intermediates. Sorry, just make sure I've got the right thing. 4B. 5. Intermediates in the Strecker synthesis include all of the following nitrogen-containing functional groups, except nitrile, imine, amide, amine. Intermediates in the Strecker synthesis include imines, nitriles, amines, and amides. What's an amide again? Amide versus amine. Amide is carbonyl carbon atom is linked by a single bond to a nitrogen atom. Amine is just nitrogen, period. With a lone pair. So I guess the point is amines are single bonds, amides are double bonds. Not with the nitrogen, though. Our imine is the double bond with the nitrogen. Our amide is nitrogen single bonded to a carbon that's also double bonded to an oxygen. And that part, I guess, is not on here, is it? By the time we get the double bond with oxygen, nitrogen's already left. Before that, before nitrogen leaves, we never have a double bond with oxygen. Even in the beginning, when we start out with aldehyde, as soon as nitrogen attacks, that carbonyl opens up. So the amide is not present. Amine is present. Imine is present. Nitrile is present. Amide is not present. 5C. A biochemist is synthesizing valine, shown below, using the Strecker synthesis. Which of the following carbonyl-containing compounds would be an appropriate starting reactant in this synthesis? So this is valine. Strecker synthesis is using our amino nitrile. The carbonyl containing compound could be an aldehyde, like an al. We used an aldehyde, so we're going to cross out the ketone, propanone, between propanal, 2-methylpropanal, and butanal. I guess the difference is how long the chain is. So in this case, we have 1, 2, 3, 4. And where does it attach? Let's take a look at our final product. So in this case, we're adding the R and 1 carbon to simplest case, CCO is formaldehyde, right? CCO. Is that also acetaldehyde? Is acetaldehyde also formaldehyde? It is, right? No, it's not. It is. No. Formaldehyde is just carbon. That's acetaldehyde. So this is acetaldehyde. And we end up with so our 2 carbons are carbon-carbon, and this is an extra carbon got added onto it. So this carbon is extra. This one is included. So this is our nitrogen carbon. The R is carbon, carbon, carbon. So carbon, 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 3 carbons plus our extra carbon, 4 carbons. It's got to be butanal or 2-methylpropanal. 2-methylpropanal, because it's got this little split. 1, 2, 3, 4. Give me 1 second. My doorbell just rang, and I gotta answer this. So I'll be back in a minute, and we'll continue. here is bedroom. I don't know. Yeah, did you treat it as a bedroom too? Usually not really, unless you guys are seeing big issues. I think I've seen it. Mostly with basement. Yeah, so you focus on basement and first floor. So we'll do that. And then, yeah. And then the bathroom, like you said, feel free. Yeah. All right. And then, do you want me to just let myself out there? Yeah. All right. You can yell at me on the street. All right. I'll hear you, but I gotta be talking to somebody else. All right. All right. So we're trying to figure out Stricker synthesis. I think we decided it's got to be a form of butanol, but not a straight chain. So really methylpropanol also has 4 carbons. 3 for the propanol plus a methyl. So this will do it. 1, 2, 3, 4. And the methyl is on the 2 carbon of the propanol. So 6 is going to be C. 7, Y is the carbon-nitrogen bond of an amide planar. 1, it has partial double bond character. 2, it is sp3 hybridized. Or 3, it has some sp2 character. It has partial double bond character, which makes it sp3 or sp2 hybridized, some sp2 character. So 1 and 3 only is D. Number 8. Which of the primary methods of amino acid synthesis results in an optically active solution? Well, I think we learned that they both do, right? Both the Strecker and Gabriel syntheses. Let's double check. I don't think I wrote that down. It's in the chapter, though. Like the Strecker synthesis, the Gabriel synthesis starts with a planar molecule. Thus, the product is a racemic mixture of L and D amino acids. So that applies to both of them. 8 is going to be C. 9, during the Gabriel synthesis, thalamide serves as the nucleophile base leaving group electrophile. It's got to be the nucleophile, right? Gabriel synthesis, thalamide. It's got a negative charge and it's going to attack the carbon, and bromine is going to leave as the leaving group. So this carbon is the electrophile. This nitrogen is the nucleophile, A. 10. Each of the following reaction types occurs during the Gabriel synthesis except A. Decarboxylation, B. Nucleophilic substitution, C. Dehydration, D. Hydrolysis. Gabriel synthesis. Decarboxylation is one of them. Nucleophilic substitution is SN2. Dehydration is not there. Hydrolysis is. Dehydration, C, is not present in Gabriel synthesis. 10 is C. 11. At physiological pH, which 2 forms of phosphoric acid have the highest concentrations? H3PO4 and H2PO4, H2 and H and PO, PO and H3. So it's the two middle ones, H2 and H, I believe. Let's double check. Physiological pH, dihydrogen and hydrogen predominate. Dihydrogen and hydrogen. 11B. 12. An aqueous solution, pyrophosphate, will likely form insoluble complexes, be stable and inert, degrade into inorganic phosphate, decrease the polarity of the solvent. We learned that pyrophosphate is unstable and it'll degrade into inorganic phosphate. 12C. Pyrophosphate is unstable in aqueous solution and is hydrolyzed to form 2 molecules of inorganic phosphate. All right, there you go. 13. What would be the charge of aspartic acid at pH 7? Neutral, negative, positive. There's not enough information to answer the question. At a pH of 7, a carboxylic acid well, they don't tell us what the pKa of aspartic acid is, do they? Let's double check. They might have given us that. Negatively charged amino acids, including aspartic and glutamic acid. So now let's go with negatively charged. 13B. 14. When a bond is created between 2 nucleotide triphosphates in DNA synthesis, the small molecule released from this reaction is nucleotide triphosphate, the small molecule released is a pyrophosphate, inorganic phosphate, ATP, organic phosphate. I guess you're taking an ATP and you're getting pyrophosphate out of it. Let's double check. It releases an ester dimer of phosphate, referred to as pyrophosphate. All right. 14A. The hydrogens of phosphoric acid have pKa values that allow high buffering capacity over a small pH range, allow moderate buffering capacity over a large pH range, allow low buffering capacity over a small pH range, do not allow buffering. It's got to be B, allow moderate buffering capacity over a large pH range. Let's look at our answers. Thanks, dude. All right. Number 1, D, 2B, 3B, 4B, 5C, 6C, 7D, 8D, not C. Both the Strecker and Gabriel synthesis contain planar intermediates, which can then be attacked from each side by a nucleophile. This results in a racemic mixture of enantiomers, and the solution will therefore be optically inactive. My bad. I said it'll make a racemic mixture, but that makes it optically inactive. Optically active is if it was a racemic mixture. So neither will make optically active solutions. Silly mistake there. 9 is A, 10 is C, 11 is B, 12 is C, 13 is B, 14 is A, 15 is B. Just to go over 8 again, remember if you have 50% of each of the two enantiomers, then they'll cancel out. If you had 70-30, then you would get some optical activity, right? But if it's 50-50, you'll get no optical activity. They'll kind of cancel each other out. All right. Well, that's it for nitrogen and phosphorus containing compounds. Next time we'll get into spectroscopy. Thanks for watching.